Welcome to Intro to Simple Linear Regression. I am Elizabeth Albright at the Nicholas School of the Environment. The objectives and concepts of this video include covariance and correlation, ordinary least squares to draw the regression line in simple linear regression, the population regression function, the sample regression function, and we will interpret the coefficients in simple linear regression. So let's first talk about covariance of two random variables. The sample covariance is a measure of how two variables, or two random variables, x and y, vary together. Here is the formula. Covariance of x and y equals 1 over n minus 1. The summation of I equals 1 to n of x sub I minus the mean of x times y sub I minus the mean of y. And again, this is a measure of how two variables, x and y, vary together. So now let's talk about the correlation coefficient. The correlation coefficient equals the covariance of x and y divided by each of their standard deviations. It is a very useful measure of the strength of the linear relationship between x and y and is always bounded by -1 and 1. 1 represents a perfect positive linear relationship, whereas -1 represents a perfect negative linear relationship. And here's our formula. R, or the correlation coefficient, equals the covariance of x and y divided by each of the standard deviations. To calculate this in R, we can use the function core. So core parentheses, the first variable, comma, the second variable. And in correlation coefficient, it doesn't matter which variable is first and which is second. So again, the correlation tells us a measure of strength of the linear relationship. And it tells us the direction of the linear relationship, positive or negative. And a scatter plot can tell us some of the same information. It tells us the strength of the relationship, the direction of the relationship, and the overall kind of shape or function of the relationship. So let's look at 4 scatter plots and their associated correlation coefficients. Looking at these 4, without looking at the titles, which ones do you think have positive relationships? All right, so the one on the upper left in green has a correlation coefficient of positive 0.99. So a very strong linear relationship there. We can tell from the scatter plot and the correlation coefficient of 0.99. Moving over to the right, the orange plot, we have a correlation coefficient of -0.9, so a negative relationship. And again, it is pretty strong, -0.9. The bottom 2 scatter plots suggest weaker relationships. The one on the left is negative with the correlation coefficient of 0.47, and on the one on the right is a positive relationship with a correlation coefficient of 0.3. And remember, the correlation coefficient ranges from -1 to 1, and it is a measure of strength of linear relationship. So now let's move on to simple linear regression. So what is a linear regression model, or sometimes called linear model? And these describe relationships among variables and allows us to hypothesize and test relationships, as well as make predictions about a response given values of explanatory variables. So with simple linear regression, we're going to start simple. Right? I always like to start simple and build up from there. So a simple linear regression has one explanatory variable and a response variable. So a response variable is y. You may have heard the term dependent variable. I prefer response or outcome variable because there's lots of meanings of dependent in statistics. I think it gets a little confusing. So the y, or the response variable, is assumed to be a random variable. It has a probability distribution given our values of x. Our explanatory variable, x, and we only have one of these in simple linear regression. Sometimes it's called independent variable. And that's assumed to be fixed. It's not assumed to have a probability distribution. So again, we have one response and one explanatory variable in simple linear regression, y and x. So let's think about correlation versus regression. Correlation measures the degree of linear association between two variables. Doesn't matter which is first or which is second, or which is x and which is y. In regression, the response variable, or y, is assumed to be random or stochastic and therefore has a probability distribution given our values of x. In regression, the explanatory variables, or x variables, are assumed to have fixed values. So let's dig a little deeper into linear regression. Linear regression lets us estimate the slope of the population regression line. The slope of the population regression line is the expected effect on y of a unit change in x. So we're interested in the relationship between x and y. All right, so two variable regression analysis. Here we have x and y. Now let's add some observations. So now we need to figure out how to draw a line that best explains the relationship between x and y given this set of observations. So we could draw a line. Oops, we lost a point, lost another point. Where are they going? There we go. We could draw a horizontal line. A horizontal line would suggest no relationship between x and y, right? So no matter the value of x, we would have the same y. We could draw a line that represents a positive relationship, such as the one here. But what about a line that would represent a negative relationship? How do we know which line best fits the data? And linear models use what is called ordinary least squares to calculate the regression line, or often uses ordinary least squares. When we get to more complex models, we will look at maximum likelihood estimation. But today we're going to speak about ordinary least squares. So what is this? Sometimes you'll hear it referred to as OLS. The error, or the residual, is the y distance between the value of the line and the observed value. We can draw the line that minimizes the sum of the squared errors. So again, the error is the y distance between the value on the line, or the predicted value, and the observed value. And we want the line that minimizes the sum of the errors that are squared, or summing the squared errors. So let's look at it here. Here we have a line, and each of the vertical blue lines is the error, and that is between the yi, or the y observed, and the yi hat, or yi predicted, and that's the y on that green line, the predicted line. So for observation 2, we have the y2, and see the red line on the y-axis, right? And that represents the y distance between the observed and the predicted value. And what ordinary least squares does is minimizes or finds the line that minimizes the sum of the squared errors. So minimizing the sum of the squared errors. So again, the error, sometimes you'll hear it called residual. That's yi minus y hat I, or observed minus predicted. And we want to minimize the sum of the squared errors. So minimize the difference there squared. So from our algebra days, we know that the equation for a line equals y equals b1 times x plus b naught. You may be more familiar with the term y equals mx plus b. So in our case, b1 is equivalent to m, and b naught is b. So where b1 is the slope and b naught is the y-intercept. So the formula for minimizing the sum of squared errors is minimizing the sum of I equals 1 to n of yi minus, now we're putting these in brackets, b1 xi plus b naught, all of that squared. And you can see here we are just substituting in bx plus b naught, which we got here, and putting that in for y predicted, right? That's the formula for the line. Y predicted, or y hat, is the value on the line, right? And we have our formula. We can use calculus then to minimize this formula and solve for b1 and b naught. So we need to minimize and then solve for the slope and y-intercept. I'll refer you to Wooldridge Chapter 2 if you want to work through the calculus. We will not worry about the calculus in this course, as it is not a calculus-based statistics course. But once we minimize, we can calculate both the estimate, or the predicted beta 1, right? That's the slope, and beta naught. Right, we've moved from b's now to betas. And hats means predicted, so our sample. And so our predicted or estimated slope equals the sum of I equals 1 to n xi minus x bar times yi minus y bar all over xi minus x bar squared. And then our formula for beta naught hat equals y bar minus beta 1 hat times x bar. And now we have our estimation of the line. Estimate of the slope, estimate of the intercept. So we have the simple linear regression model, yi equals beta naught plus beta 1 xi plus u. We have n observations, x sub I, y sub I equals 1 to n. X is the explanatory variable, y is the response variable, beta naught is the intercept, beta 1 is the slope, and u is the error term. We will talk a bit about this more in the next couple videos or in class. But we are assuming that on average the error term, that u equals 0, and that on average or expected the value of u given x equals the expected value of u. So u is not conditioned on or dependent on the value of x. And we will talk about assumptions, but not in this video. So let's talk about the error term. The regression error consists of omitted factors. In general, these omitted factors are other factors that influence x other than the variable, or that influence y other than the variable x. The regression error also includes error in the measurement of y. So now let's put some numbers to this. Hopefully things will become more clear. And we're going to talk about daily family income and consumption or spending, daily spending. So daily family income and consumption for a population. We are going to pretend that we know the income and consumption or expenditure for a whole population, a small town here. And we have our set or fixed values of x that range from 80 to 260. Those are in orange at the top. And then given x, we have daily family consumption going down. So those are our random variable y, or our family consumption given family income. So for example, at income of $80 per day, we have 5 observations. We could calculate the conditional mean, the expected value of y given our x, and we could calculate that at 65. All right, and we could do that for each of our values of x. And remember, our x, or our explanatory variable, is fixed or assumed to be fixed, and our y in this case is daily family consumption expenditure, and that is assumed to be a random variable given the fixed value. So what I have done here is plotted those observations. And this again is the observations from the whole population. Typically, we do not have all of the observations of the population. I'm doing this as an illustrative example. So we have values of x and values of y. Again, we are assuming that x, our explanatory variable, is fixed. And then we have a random distribution of daily household spending or expenditures given a value of x. So population regression line. It assumes, again, as I said before, that y is a random variable given different values of x. We're assuming that values of x are fixed. And the population regression function or line goes through the conditional means of y given values of x, or E of y given x. So here are those conditional means that were calculated on that list of observations, or on that page that listed all the data. And you see the yellow, and those are the conditional means conditioned on the value of x's. And our population line goes through those conditional means. And in this case, the function or the equation for the line is 0.6 income plus 17. So our slope is 0.6 or 60 cents or $0.6, and our intercept is 17. And so our population is fixed but unknown in the typical world of statistics, right? It's knowable but unknown. And what we typically do is draw a sample, oftentimes randomly, from the population, and then we infer back to the fixed but unknown population. So we use a sample regression model or regression function to say something or to infer back to our population regression model. So the population regression function is the expected value of y given x equals beta naught plus beta 1x. X is the explanatory variable, y is the response variable. E of y given x is the expected value of y given x. Beta naught is our intercept, and beta 1 equals our slope. And this is a population regression function. So on the left side of our population regression function is that expected value of y given our x's. You will notice that in the model we talk about betas, Greek symbols, to represent the population, slope, and intercept. So now let's randomly sample from our population. Now we're going to shift to sample regression function. Here is our population again, and we're going to sample across those values of x, sample y's, and we pull two samples, sample 1 and sample 2. Here is our sample 1, where we get y hat equals 0.509 times income plus 24.5. Sample again, and we get y hat equals 0.576 times income plus 17.2. So why are these numbers shifting? Right? We know what our population function looked like. But now we have pulled two different samples, and every time we randomly sample, whether that's a t-test, comparison of means, etc., there's sampling error. Our samples are going to vary, right? And so as a result, our slope and our intercepts will also vary. Therefore, our estimates will have standard errors associated with them. And the linear line, the regression line, will also have an error, root mean square error. And we will talk about errors in inference in our next video. But for now, let's focus on the interpretation of coefficient estimates. So our simple linear regression based on our sample now is y hat. We have shifted away from the expected value of y given x. That's how you write the population function. For a sample, you write y hat, or predicted y, equals 0.509 times income plus 24.5. I'm just taking one of the samples that we pulled, just as an example. So interpretation is a unit increase in x is associated with a 0.509 unit increase in the predicted value of y. In other words, a $1 increase in daily income is associated with an approximately 51-cent increase in predicted daily spending. Our beta hat 1, and we are using hat because it is estimated from our sample, and it is not the population coefficient, right, is 0.509. And our beta hat naught, or beta naught hat, is 24.5. So again, what this means here, that summarizes the relationship between income and expenditures, is a $1 increase in daily income is associated with a 51-cent increase in predicted daily spending. So how do we estimate the line or the slope and the intercept given a sample or a set of observations of x and y in R? This is what this slide shows. What I've done here is type in the observations for income.sample1 and the observations for spending.sample1, and then put them in a data frame. And I'm just calling the data frame sample.1. In the second chunk, which I'm calling lm.1, I am naming the object lm, short for linear model.1, and using the linear model function, or lm, parentheses, our y, and our y is spending.sample1, tilde, our x, and our x is income.sample1, comma, data equals sample.1. end parentheses. And then I call the object lm.1. When I call the object lm.1, I get these results here, and it calculates the coefficients. The intercept is 24.4545, and the slope is 0.5091. That is our estimate of the slope. 24.4545 is our estimate of the y-intercept for the sample that we entered above. In our next video, we will talk about standard errors in inference, about going from the sample estimates to say something about the population. So to recap, we have correlation, which is a measure of linear relationship. We have simple linear regression, and that includes or builds on the error or residual yi minus y hat I. And we use ordinary least squares to draw the function or the line between x and y. And that line is what minimizes the sum of the squared errors. We have a population regression function, and this goes through the expected y given x. The relationship between the populations of x and y is typically unknown, but it is fixed. Right? And from our sample estimates, we can then infer back to our population. Again, we are not doing that in this video today. We have a simple linear regression model, and we can interpret the slope. We could also interpret the y-intercept. It is typically more common to interpret or focus on these slopes, or the coefficient estimates of the slopes. A simple linear regression, we have one slope. And that concludes the major concepts for today's video. Thank you very much for joining in. Again, I'm Elizabeth Albright at the Nicholas School of the Environment.